everyone, my name is Sadie and welcome to Resonance Tutoring. Today I wanted to talk to you about a common chemistry concept that students can sometimes have trouble understanding, the mole. So maybe you've got the number memorized, maybe you know it as the Avogadro number, maybe you can do a little math with it, or maybe it's completely new to you. Either way, in this video, I'm going to give you a more concrete understanding of what a mole is and why it's useful for chemistry. So basically, a mole is just a specific number of things. 6.022 times 10 to the 23rd things, to be exact. And that's a really big, intimidating number, but it's not much different than saying a dozen to mean 12 things. So a mole by itself is just a number, just like a dozen. If I tell you I have a dozen, maybe I have a dozen eggs, I could also have a dozen donuts. Unless I'm specific, you just know that I have 12 of something. And a mole works the same way. Mole just means 6.022 times 10 to the 23rd. Usually we're talking about molecules of something, but we could also be talking about atoms or electrons. So that's why it's important to be specific. So the reason that it's important to use moles as a unit is because there are an unfathomable number of molecules in our universe. Let's take a sugar cube, for example. It's made of sucrose. I could tell you that there are 7 sextillion molecules of sucrose in this sugar cube, or I could tell you there are 0.01 moles of sucrose. Personally, I'd rather do math with that second number. Kind of like how if you have a business that makes hundreds or thousands of donuts in a day, it gets easier to just start counting them by the dozen. So why 6.022 times 10 to the 23rd? That seems kind of random, right? Like, how did Avogadro even come up with this number? Well, the short answer is, he didn't. Yeah, no, it's named after him, but he didn't even discover it. It was actually estimated years later by some Austrian guy, and even then it wasn't proven and corrected until some American guy did more experiments. In fact, not everyone even agrees on who the number should be named after. But that's just scientific discovery for you. The history of how we figured out this number is pretty complicated, but I'm going to link a really interesting Scientific American article about it in the description below. All you really need to know is that 6.022 times 10 to the 23rd is the number of atoms in exactly 12 grams of carbon. So it's as good a place as any to set as a reference point. And here we're getting into the relationship between moles and mass, or weight. Now technically mass and weight are different, but I'm going to let the physicists be picky about that one. So some molecules are small and light, while other molecules are bigger and heavier. I think we could all agree that a dozen feathers is not going to weigh as much as a dozen bricks. Likewise, a mole of water is going to weigh less than a mole of octane, and we can prove it using their molecular weights. So every molecule has a molecular weight, which can be calculated by adding up the mass of each atom in the molecule. In the instance of water, we have 2 hydrogens, which each have an atomic mass of 1, and 1 oxygen with an atomic mass of 16. This adds to 18 grams per mole total, which means 1 mole of water should weigh about 18 grams. For octane, we have 8 carbons and 18 hydrogens, for a total of 114 grams per mole. Same number of molecules, 6.022 times 10 to the 23rd, but this one's much heavier. These are both a dozen, but this one is heavier. So how does this help us do chemistry? Well, for one, it's crucial to making sure that your reactions are balanced. You may have already learned how to balance a reaction in your general chemistry class, adjusting the coefficients on both sides until you have the same number of atoms on each side of the equation. So this equation tells us that 2 molecules of sodium chloride will form 1 molecule of sodium sulfate. Likewise, 2 moles of sodium chloride will form 1 mole of sodium sulfate. And that's all well and good on paper, sure, but what if you wanted to actually run this reaction in a laboratory? Okay, please go measure out 6.022 times 10 to the 23rd molecules of salt. Yeah, just count them one by one. It's impossible, right? So we have to be able to link moles to something that we can actually measure in the physical world, and that's mass. If we know that sodium chloride has a molecular weight of about 58 grams per mole, then we can easily just walk over to the balance Scoop out 58 grams of sodium chloride and rest assured that it's 1 mole. It's a lot of salt, but you get the idea. So that's the basics of the mole. We can go more in depth with the uses of molecular weight in another video if people are interested. But otherwise, thank you for watching. Thank you for giving me an excuse to buy some donuts. If you found this video helpful, please like, comment, and share. And if you're interested in an online tutoring session with me, I'm going to put my contact information at the end of this video.